Let's take a look at this problem from your homework assignment. And this problem is asking us to find the flux integral of a given vector field on the oriented surface S. And your vector field is x, y, 9. And your surface is going to be the boundary of the region enclosed by a cylinder and a couple of planes. So our cylinder is x squared plus z squared is equal to 1. So that looks like it'll be, we can start with a circle on the xz plane, and then it's going to go towards the y-axis. It has 0, y is equal to 0 as one of the boundaries, and then you're going to be in this cylinder, and then there's a plane. X plus y is equal to 5. So x is equal to 5 in the x-axis, y is equal to 5 in the y-axis, and that it's going to be a line in the xy plane, but it's going to cut the cylinder at some sort of angle, and so that's how it's going to look like. We can view this in our calc plot program. So this is the vector field that we're looking at. It's x, y, and 9, so it looks like it's always going to be going up. And it's going to go x, y, in the x and y directions. So when y is equal to 0 or when x is equal to 0, it just goes straight up. And anything else outside will be a little bit slanted, but it's still going to be going upward. We have the surfaces. This is one of the surfaces. Let's take out that vector field for a moment. This is one of the surfaces. It's that cylinder that has been cut off. So on the xy or xz plane, it's just flat, but it's going to get cut off and give you a little bit of an angle and the cutoff. And so there's going to be a covering on both sides. We have the cover for the front part and a cover for the back, which we'll see in a second. There he goes. So this is the closed surface that we're dealing with. Because it's a closed surface, we want to make sure that we have an outward orientation. So we can take a look at the normal vectors associated with each surface, and it should be going, the normal vector should be going outward. Okay. All right, so let's take a look at our problem again. Now that we have a general idea what the surface looks like, we know that we have 3 surfaces, and so we need to parameterize each one. And the first one that we'll deal with is that disk on the xz plane. So surface 1 is going to be the disk x squared plus z squared is less than or equal to 1 on the y is equal to 0 plane. Surface 2, let's call the cylinder surface 2. It's going to be x squared plus z squared is equal to 1. That's the cylinder. And so we need to find restrictions on the y. So the y is just going to go from 0 to, well, it doesn't go, if this was a constant, then it'll stop at a constant, and that means we would be describing just a regular cylinder. But since this thing gets cut off at an angle, this needs to be described as where it gets cut off. And so it gets cut off at the plane x plus y is equal to 5, and so we want the y value of that. So if you solve for y, you get 5 minus x. So this is going to be your limits. This will help us find our limits of integration. And then our S3, let's put S3 over here, and then we'll move it a little bit later. But S3 is going to be the disk. So you got all this other stuff. It's this disk over here. And so that disk is really coming from a plane. So we can describe S3 as the plane x plus y equals 5. But then our domain is going to restrict us within this disk. So our domain is going to be x squared plus z squared is less than or equal to 1. We will deal with this a little bit later. Let's tackle the first two surfaces first. So by the way, the bottom line here is that if you want the flux of this vector field over these surfaces, you have to add the flux integrals of each of them. And so we will find the flux of each, and then we'll add it at the end. All right, let's work with S1. So S1 over here is this disk. Let's start with a parameterization. Our R. So it looks like I can just deal with X and Z. So let's just deal with X and Z. And our X is going to be X, our Z is going to be Z. So those are the independent variables. Now we need to figure out what our Y is. So this is just up along the plane. Y is equal to 0. So y is equal to 0 just means that we're going to be at 0 here. The fact that this is coming from a plane that is one of the coordinate planes, the xz plane to be exact, we can take advantage of another way to express our flux integral. And another way to express our flux integral is with a normal vector n. So let's first find our normal vector n, and the unit normal is going to be pointing in the negative y direction. So if I let x and z equal to 0 and y equal to negative 1, I have my normal vector that I want. And then let's just remind ourselves that the flux integral can be rewritten as a double integral over some domain D of f dotted with n, the normal vector. And then this becomes a surface integral. Oh, I suppose we should still call this S because this is still a surface integral. But in any case, what we want to do is we want to take this dot product and compute this. So I need to figure out what F is. So F is x, y, 9 dotted with n, 0, minus 1, 0. Oh, we also want to make sure that we put this parameterization into F. So F of R of xz dotted with n is going to be x is x, y is 0. So this is going to be our big advantage. And then z is equal to 9 dotted with 0, minus 1, 0. And this is going to give us 0. So now if this whole thing, if f dotted n is equal to 0, then the whole thing is going to be equal to 0. So our first surface, the flux over our first surface is going to be 0. All right, so that's good. Now let's work with our second surface. So the parameterization of this will be parameterizing a cylinder. So when we parameterize a cylinder, we can use the cylindrical coordinate parameterization. And the cylindrical coordinate parameterization will be dependent on r and theta. But I want to change this idea. This also dependent on the variable that the cylinder is running along. So it's running along the y-axis. So r, by the way, is going to be fixed because the radius of the cylinder isn't changing. So the r is just going to be equal to 1 for the polar coordinate or cylindrical coordinates. So that's constant, and so this is really just dependent on y and theta. So our x and the z are the ones that's going to make up the circle. So the radius is 1 cosine theta for the x. Our y is just going to be the y, and then our z is going to be 1 times sine theta. Now, our given domain here is going to be limits for the theta variable, which goes all the way around from 0 to 2 pi, and limits for the y variable, which we've already identified as going from 0 to 5 minus x. Now, unfortunately, I don't have an x in my parameterization, but I do have an x defined by y and theta, or just theta in this case. So instead of x, we're going to use cosine theta. So this will be our limits of integration. Before we move on, we need to figure out what r y is and r theta, because we need to find a cross product of them. This will give us our normal, and this is where we're going to be able to check our orientation. So ry, the derivative of the parameterization with respect to y, and thetas are constant with respect to y. And so I just have 0, 1, 0. And then with respect to theta, I have a negative sine theta for the first, and y is constant, and cosine theta for the last. So ry cross r theta will determine our orientation. And if we do the cross product, the first term is going to be cosine theta. The middle term is, it looks like it's going to be 0. And then the last term is going to be 0 minus negative sine theta. So that's positive sine theta. So this is my cross product. Now I need to see if this is going to be, this is going to preserve the orientation. For that, I will take a look at what's happening in the, I know my y is equal to 0, so I'm not going to worry about the y-axis. I'll just take a look at the x and the z-axis. And if I have a circle in x and the z-axis, which is what we have here, the cylinder is really just circle. And if I pick some random point with some random theta, this is going to be cosine theta in the x and sine theta in the z. And then my normal vector will be exactly the same. So from here, I can just draw that same vector. And so imagine that vector going out like this from the cylinder. It looks like I will have an outward orientation. So this preserves our orientation. So this is an orientation preserving parameterization, which means we'll go with it, we'll leave it as is and not have to worry about negative signs. So the other thing that we need is going to be f evaluated at r, and in this case our independent variables are y and theta. So x is x, so that's cosine theta. Y is y, and z is 9. And so this is going to be our function. Now we want our function evaluated at y theta, and then we'll dot that with ry cross r theta. This will give us our ds. And so the dot product is cosine times cosine, cosine squared theta. The dot product is going to be a scalar. So I'll put a plus sign. Y times 0 is 0, and then we have 9 sine theta. So this is our integrand. This is the thing that's going to go inside of the integral. And so let us write our double integral, or our surface integral, of S2 dotted with ds. So this is going to be a double integral now over the domain. I think we identified the domain here of this thing, cosine squared theta plus 9 sine theta dA. I was wondering if we could probably go to polar, but I don't think that would make sense here in this case. So let's just continue on. We can actually now set up a double integral of cosine squared theta plus 9 sine theta. And then we can call this dy. I would put the y in first because y is dependent on theta. So this is going to go from 0 to 5 minus cosine theta, and then d theta, which is going to go from 0 to 2 pi. All right, so let's put that into our Wolfram or symbol lab and then get our answer. Okay, so our integral gave us a 5 pi. So we're going to contribute 5 pi to this through our S2. So we'll keep this aside, and now let's take a look at our third surface. Our third surface is this little bit over here. This little portion, this little slice. And so let's find a way to parameterize that. It looks like it's a plane with an x and a y, and it looks like it's going to be based on this disk over here. So for us to parameterize that, let us just parameterize this as if x and z are independent again. So we'll start off our parameterization as a graph parameterization with x and z. And then realize that we are going to have a domain that's going to be the disk. And then now we need to replace our y, and we will realize that this is the plane x plus y is equal to 5. So if we solve for y there, y is going to be equal to 5 minus x. So that is our our parameterization. And because of this domain, we will probably change this into polar, but we'll do that a little bit later. So let us continue on. We need to figure out what Rx is, and with respect to x, this vector is going to be 1, comma, negative 1, comma, 0. And then with respect to y, oops, that's with respect to z, it's going to be 0, 0, 1. So let's take the cross product to see if we're going to have the correct orientation. So the cross product is going to be negative 1, comma, and In the y, it's going to be negative, negative, and then in the z is going to be 0. So if I'm looking at this, well, maybe if we can do this in 2 dimensions, it's kind of easier to see. If we take a look at this in 2 dimensions, and the 2 dimensions would be eyeballing it from above the y-axis. So we would look at this from x and z. And this is the domain that we have. And so pretend that the plane is right at you. And it's going to be pointing along the x and the y. So it's going to be, well, this is probably a little bit difficult to see, but maybe we will go back to the 3 dimensions, and it's going to be negative 1, negative 1. So I think from here it's going to be pointing in a negative x and a negative y direction. So that looks like it's going to be the opposite of what we want. So this reverses the orientation. So orientation reversing parameterization. So the fact that it's reversing means we're going to need to compensate this with a negative 1. Okay, so now we have that, and let us go back to our vector field, and we'll put the parameterization that we have into the vector field. So the x is equal to x, the y is equal to 5 minus x, and the z was just equal to 9. And so now let's take the dot product of this vector that we just found dotted with Rx cross Rz, our orientation reversing parameterization. So the dot product is going to be x times negative 1 plus, and then we have another negative 1, 5 minus x, and then 9 times 0. So we have a negative x, negative 5, and negative, negative, so it's positive x. So this is just going to be negative 5. All right, let us set up our integral. So our flux over the surface, this is the third surface now, of f dotted with ds is going to equal double integral over the domain. Again, our domain is going to be this circle, this disk. We'll deal with that in a minute. We have the dot product is going to be negative 5 and dA. Now, don't forget that we have an orientation reversing parameterization, so we need to multiply this by negative 1. Okay, so let's continue on. And the negative 5 and negative 1 is going to be positive 5 on the outside. This is the integral of 1 dA. Well, if you remember, a double integral whose integrand is 1 is going to be just the area of the domain. This domain is a disk of radius 1, so the area is going to be pi r squared. So that's just equal to pi. Pi. So now that we have that, we can summarize everything. We have, according to what we had, a flux integral over all the surfaces is going to be the flux over S1 plus the flux over S2 plus the flux over S3. The flux over S1, we got that to be 0. The flux over S2, we got that to be 5 pi. And then we just finished this last one. The flux over S3 is 5 pi. So total 10 pi. Okay. So I hope this works out. I hope this helps. And good luck with the rest of your homework.